to see on a board. And some of you were getting there or close to there, but I just, after an hour, I wanted to call it. So, first of all, this team said the volume of the container was they're gonna live on the edge, y'all. They're gonna fill it with 7,200 cubic feet. And you know why? Because Fig MH is fake, so they don't care. They're going to the edge, 7,200 cubic feet. Now, let's kind of unpack all these pieces, because you've been thinking through all of this. The side areas, so the area of the three main sections, the area of that, like a cylindrical surface area, 2 pi r, which is the circumference, times the height. Now you guys, I've been bugging you around the room to make sure it's clear, and this team I want to hear from you. In both cases, where's the height? In this drawing, Keith, where's your height?
It's the full length of the cylinder.
This is the height, right? And why this is important is some of you were similarly doing things like this and hadn't really thought that when you do, like for instance, pi r squared h, you're saying h is that whole length. But then when you came down here, you were saying h was this, and you were thinking you had 3 of them. You were mixing up the meaning of h. Sometimes h was this, the whole length, and sometimes h was the smaller sections. You can't do that. H has to be the same thing throughout. So an important part of your analysis, especially when you're modeling like this and you're building formulas and such, is to define your variables. Make sure everybody would know, if you were doing this professionally, I know this is just some silly James Bond thing I wrote, but if this was real life stuff, you would need to have clear definitions of variables so everybody knew you were talking about that whole thing. All right, so given that that's true, pi r squared h is the volume of the whole thing, has to be 7,200, they're living on the edge. The side area, 2 pi r h, and that's the whole side area because they didn't break it into three sections. They treated it as if it was one. The end caps, a pi r squared on each end. So you got 2 pi r squareds. And then the welding. All right, Jackson. When you weld, for instance, this piece, somebody tell me if Jackson's looking.
I'm looking.
Jackson, if you weld this piece to this end cap, wouldn't you have to weld like a bead around that whole circumference to keep it all together?
Yeah.
And then you'd have to do the same thing. I know you can't really see it, but wouldn't you have to weld the whole circumference here, and then also on the end?
Yeah, but also depending on the thickness, that determines how many welds you need to do for it.
Yeah. And we're just, I don't know, simplifying this a lot and just saying somehow you're welding around the whole thing. And so how many circumferences do you have to put all 5 pieces together? 4. There's 4, and circumference is 2 pi r. So 4 2 pi r's is the 8 pi r. So we really need these 3 pieces in order to do our job. Hey, what was the job? Minimize what?
Cost.
And Enoch, because I messed with your brains here, by not having a uniform cost, and including welding too, it is not the case with this situation that minimizing the surface area will also minimize the cost. It may not. And so what we needed to do is to build a cost equation and say, all right, the cost, now look, $20 per square foot times how many square feet do we have on those middle 3 sections? 2 pi r h. So $20 a square foot times that many square feet. $35 a square foot for that many square feet on the end caps. And then $1.50 per foot times that many feet worth of welding. Now, Bo, I know you guys did it a little differently, but I want you to just kind of track with what they did here. How many different variables do you have in here?
1, 2.
There's 2. There's an R. Believe it or not, that's an R. There's an H. There's an R. There's an R. So there's 2 different variables, R and H.
H is defined. Doesn't it become a constant now?
It's not a constant. It's going to be whatever is going to minimize the cost.
Okay.
When we're done solving this thing, cost, if you make R really small, H is probably going to be really big. Like a long, skinny tube in order to hold 7,200 cubic feet. That thing's going to cost a lot. So you make R a little bit bigger, that's going to make the cost minimized. But then if you make R too big, then like this big wide tube, the cost goes up once again. So there is a minimum cost, and we'll figure out what H will be later on, I think. Did you guys do it, Keith? CC?
Yeah, it's in green to the left.
Ah. So in their case, the radius, it's an R, by the way. You have to learn with Keith. When you see a V, assume it's an R. Unless you otherwise figure out that it's a V. R is 8.6 feet, the height is 30. So, right now, R varies, which makes the cost vary. And then H would vary as well, but Bo and I were having a chat, a reminder of when you have two variables that determine the cost, you gotta wait for Calc 3 to figure that one out. Come back in a couple semesters, we'll solve this problem again, if I remember, using Calc 3 techniques. And then you can decide, would Calc 1 be easier, would Calc 3 be easier?
It's gonna be Calc 3, isn't it?
It's good.
Oh, I mean, once you learn it, yeah. I mean, right now it wouldn't be, but once you learn Calc 3 stuff, yeah, probably. So, we have to figure that out. So what's our little thing you learned about that? Well, if the volume has to be 7,200 cubic feet, then you can just algebraically solve this for H by dividing by pi r squared. And so now H has to be this. Whatever R turns out to be, H is going to have to be 7,200 divided by pi times that R squared. And so we can replace H. Where did you guys do that at, right?
It's kind of hidden.
It's kind of hidden. So that H right there now got this. And they did some simplifying. There too. All right, so the cost equation is here. You guys, that's not going to go through all the gory details. They did some simplifying, but then look. First derivative test, Joel, that was you, right? Earlier today? What does the first derivative test tell us to do?
Set it equal to 0 and
Set it. What's the it?
set your derivative equation equal to 0.
So they found the derivative, C prime, assuming that the cost, you just went C for cost. And you took the derivative C prime. You took C prime, and you found out, you kind of skipped that step here too, but you set it to 0. And then you did some algebra, but the algebra got a little yucky, didn't it, Keith? CC. So what did you guys do in 2025? You went to Wolfram Alpha. You said, hey, Wolfram Alpha, help me out here. Because I don't know if you guys can see it. Maybe you can kind of see it in this step, but if you distribute that r squared, you'd have something r cubed plus something r squared. You basically have a cubic equation. It's not quadratic, it's not linear, it's a cubic. And cubics are just harder to solve. Like I said, even back in 2000, we had technology, so I could make these projects a little bit, more realistic and more interesting to solve because we have technology to do some of that grunt work for us. So the technology came into play, and whammo! The tank should be about 8 feet and 8 inches, 9 inches. 8.5. Yeah. I mean, if you're gonna go measure it, you're gonna probably go 8 feet 9 inches instead of 8.6552 feet. All right, so that's the radius. So a 16-foot diameter. It's a pretty big tank. Go look if you're, you don't really see them around here that much, but the big, up north they have more gas, things like that. But go look at those big gas tanks that they have where they store the main stuff. And a 16-foot diameter wouldn't be that crazy, I guess. And then a height, and by the way, height is really this length here of about 30 and a half, say 31 feet. And if you build it that way, 50 grand, ain't nothing for bond. Who's paying for that? I guess it's the British taxpayers. Derivative is 0 on this cost function right there at the minimum. Did you have a first derivative? Is that you guys over here?
That's us.
You guys, oh, there it is. Your first derivative is 0 at 8.6, just like you said. Second derivative is on the positive side. And if your second derivative is positive, what does that tell us about this function if it wasn't 2025?
It's a
Concave
minimum.
what? So positive second derivative, concave up function, so we can kind of confirm that we do indeed have a minimum. What else? What's on your mind? What are you thinking? Big picture wise, what are you thinking?
Where did they find the height? I just don't see the.
I don't know where they did it, but they came back to here and they took out their.
Like,
Yeah,
where
where
they
they-
did it out.
Sometimes
use
like
it
the
on
map
calculator.
off to the side.
Oh,
Where am I looking
Because
at?
it's swinging.
The little angle.
Oh, over here?
Yeah.
Oh, it's over here.
That was the map. for
That's your
the
cost.
simplification. That was the simplification
Oh.
between.
Yeah.
I guess we
But
probably just did it.
We did it, yeah.
You might have just done it on a calculator, but here, Range, what would have happened was they took 8.6552, plugged it in for R, crunched the numbers and got H.
Yeah.
And apparently, I'm trusting them. I'm trusting them. I don't know. I haven't fact checked that 30 feet.